Hello, and welcome to today's WJE webinar. My name is Liz Pimper, and I'll be your moderator for Measuring the Invisible, Whole Building Air Leakage Testing for High-Performance Buildings. During the next hour, building science and air leakage testing experts Justin Boone and Bill O'Brien will provide an overview of whole building and diagnostic air leakage testing, including testing principles, equipment, procedures, and commonly referenced standards and metrics. This presentation is copyrighted by WIS Janney Elsner Associates, and now I will turn it over to Bill to get us started. Bill?
Great, thanks Liz. And thanks again everyone for taking the time to join us for Measuring the Invisible, Whole Building Air Leakage Testing for High Performance Buildings. And these are the learning objectives that we'll be discussing throughout the webinar. And for the outline of topics, we'll first start with some background, including what's an air barrier and why does air control matter? Then we'll get into why whole building air leakage testing is done and the benefits of this quantitative and compliance type testing. Next will be the how and how testing is performed and the theory and mechanics behind it. After that, we'll discuss diagnostic testing and how we find and detect air leakage sites specifically, and when this investigative type of testing is useful and complementary with quantitative testing. We'll also talk about case studies from our field experience, and then some overall tips for testing success and items to consider during design and construction. And we'll end by fielding questions from our audience today. We understand that the audience consists of people from many different professional backgrounds. In this presentation, we'll get into more of the technical aspects in the topics earlier on, which may be more familiar with the architects, engineers, and contractors, and we'll be offering some specific takeaways for property owners and managers later in the presentation as well. So first off, let's talk about the air barrier of a building enclosure and why is air controlled and why does that matter? Zooming out a bit and to put things into perspective, there are four primary control layers of the building enclosure. The enclosure that is composed of roof, walls, floors, and foundation. In order of importance and performance needs of the enclosure, the first and most important is control and management of water with a water barrier. It is most critical to stop water leakage. The second is control of airflow with an air barrier, which we'll be focusing on today. The third is to provide thermal resistance with a thermal control layer, such as continuous insulation. And the fourth is to know when and where a vapor control layer is needed to control for vapor diffusion. So, focusing on the air barrier, and we're going to be saying air barrier a lot. An air barrier is defined as one of multiple control layers used to separate one environment from another. Is intended to control airflow between the interior conditioned spaces and the exterior, or other types of adjacent spaces that are conditioned differently. Air leakage from exterior to interior is infiltration, as shown with the green arrows in this graphic through an enclosure wall roof, and air leakage from interior to the exterior is exfiltration, as shown with the yellow arrows. The challenge with air leakage is that it only needs unintended openings through an air barrier and a pressure differential to occur. There will usually always be a pressure differential across the building enclosure, caused by wind, mechanical systems, and/or stack effect. So the important part is getting the air barrier continuity right. Here's a photo on the left from an investigation that WJE performed at a hospital where condensation was occurring during the wintertime in the parapet, causing interior water leakage and corrosion deterioration of materials. This second photo shows warm, moist air from the interior was leaking into the parapet where it shouldn't be, through large gaps in the air barrier at roof-to-wall intersections, causing this condensation. This invisible air leakage was detected with our smoke pencil shown here. overall, the challenge is that this invisible air just needs a void and path to cause trouble. And identifying the air barrier in these important locations for continuity is so important. And even if there's a long path, like shown in this maze image right here, as long as there's a void, air will get through it. Here's another scary photo. This is from a hospital in South Florida that WJE investigated. This problem was caused by air leakage. Air leaks were infiltrating through the exterior precast concrete cladding panel joints, which allowed exterior warm, moist air to infiltrate to the air-conditioned interior, and coupled with the vinyl wallpaper, there was significant organic growth at the exterior walls and interior partition walls, as seen on the right side of this photo, due to uncontrolled airflow. Note that this is an example of a hot, humid climate issue during the summertime, and the previous example was a cold climate issue during the wintertime. So air leakage moisture problems can occur in different climate types. Why does air leakage matter? Well, the first main reason is that airflow carries moisture. Moisture can cause all sorts of nastiness, particularly when it condenses into liquid form, and particularly if it occurs where it shouldn't, on construction with non-resilient materials, more moisture-sensitive materials that can degrade easier when exposed to moisture, as seen in the previous photos and examples that were shown. In contrast, vapor diffusion is the slow molecular movement of water vapor through pores in the materials themselves, with flow from higher to lower vapor pressure spaces, driven by temperature and relative humidity differences. Air leakage matters so much more compared to vapor diffusion. Previous studies showed that air leakage flow through a small hole, such as the image on the right side of this slide, carries about 100 times the amount of water compared to vapor diffusion through this area of the material shown on the left side of the image. However, even more recent studies have shown it's actually worse than originally thought, with this airflow through this gap shown on the right side of the image is actually transporting about 200 times more water than the vapor diffusion process. Why else does air leakage matter? Well, the second main reason is that air leakage carries odors, contaminants, and air leakage can lead to poor indoor air quality. This is especially important in critical environments such as hospitals and operating rooms and laboratories, but also for building tenants and occupants in general. If someone is by a window and there's an uncomfortable draft because of an air leak, that space may not be functional. This image here on this slide shows New York City during recent summer wildfires. Continuous air barrier is desirable to adequately separate the interior spaces from the smoky exterior air and allow air control through intentional mechanical openings with designed filters. The third main reason why controlling air leakage is important is to reduce energy usage. Note, not only does air carry a lot of water, but it carries a lot of heat too. Building owners spend a lot of money conditioning space and don't want energy usage and costs to increase with escaping air leakage. Here's an energy modeling simulation study of a 6-story building, code compliant, and the only thing that was changed was air leakage. The top horizontal axis is air leakage rate. The left vertical axis is percentage change in heating demand, and the vertical green dashed line in the middle of the graph is the baseline code compliant air leakage rate. The building with double the rate of air leakage compared to the baseline has about 50% more heating demand and increased energy usage compared to the baseline building. There is a noticeable and significant impact of increased energy usage due to air leakage as proven by this study. Air control also impacts HVAC system size. So the less air control, the larger, more expensive HVAC systems are needed in a building. Here's an image of an energy comparison tool from the Department of Energy at Oak Ridge National Labs. This is a useful order of magnitude tool for any user or owner to determine rough approximate energy savings from a reduction of air leakage. The online link is shown at the top of the slide, which is available to anyone from an online webpage. This view is of the input screen, where a user can pick a location in the US, pick a standard building type, one air leakage rate, and then pick a second air leakage rate, such as one that's reduced or improved. And then here's a view of the output screen. With a reduced air leakage rate, this shows that cost savings in fuel and moisture transfer reduction shown in these two red boxes is significant. This is a rough order of magnitude estimate based on generic building types. A comparative energy modeling analysis effort could be a deeper dive in evaluation in potential energy savings for project-specific potential enclosure retrofit options and associated project-specific air leakage rate improvements if needed. Understanding energy usage and potential savings is becoming more and more important recently as energy costs have really gone up, for example, with more data centers and AI usage. So why whole building air leakage testing? Zooming out a bit again, this is an example of a project flow diagram for new construction and tasks to ensure a successful air barrier system on a building from a consultant's point of view. And the earlier the involvement in a project, the better. Starting off at the pre-design phase, the review of the owner's project requirements is important. Are we getting off on the right foot with owner expectations? Moving into the design phase, review the basis of design from the architect is important, and review and checking if the intended air barrier performance design is aligning with the owner expectations. Again, in the design phase, the review of construction documents. Trying to catch any potential issues early in the design drawings and specifications first is beneficial. For example, verifying that there is a dedicated, defined, and continuous air barrier. Moving next into the construction phase, review of contractor submittals is important. Is there coordination between the trades, including at interfaces between enclosure systems? Are there air barrier shop drawings? Next, the mock-up review is important. Constructing and testing a mock-up with an air barrier to review installation and testing performance before implementation on the building is very beneficial. Then periodic site visits during construction and testing to validate performance is important. And this is where whole building air leakage testing occurs, once the entire air barrier system is installed. Hopefully all these other quality assurance and control items occurred before whole building air leakage testing. And then once the enclosure is complete, there's usually a pre-warranty site visit and closeout report. The benefit with working with an enclosure consultant or commissioning agent is that an enclosure consultant can not only perform and observe testing, but can provide this continuity of all these services throughout an entire project. So why do whole building air leakage testing? The first reason to do it is to evaluate the performance of the air barrier by getting a quantitative number value of the air leakage rate through it. Less air leakage means a better performing air barrier, including for the benefits discussed earlier, such as managing moisture, reducing condensation risk, improving indoor air quality, and reducing building energy usage. The second main reason is to identify enclosure air leakage sources and sites through diagnostic testing. Diagnostic testing helps highlight the areas of air leakage so they can be remediated before they become covered up with cladding and potentially become a problem in the future. We have several different diagnostic test methods at our disposal two we most commonly use are infrared thermography and theatrical fog, in conjunction with the differential pressure that can be produced from the whole building air leakage testing equipment, which Justin will discuss further later. Both allow us to visualize locations of air leakage, and we also have other diagnostic tools which are for more local areas, such as smoke pencils. The other reason to do the testing is the codes may require it. Overall, energy codes have evolved and continue to evolve, and requirements differ from state to state as shown in this graphic. Some states don't have any requirements, and overall requirements vary by project location. This map highlights the applicable ASHRAE 90.1 energy code if it's required in the vintage year. The requirements of the code can differ depending on the code reference year. Overall, whole building air leakage testing is required by some states. Since the code requirements vary by location, the target acceptable air leakage rate for testing is different depending on location as well. Acceptable air leakage rate is defined as cubic feet a minute, CFM, per square foot. And Justin will get more into unit terminology later. Also, just because you don't make the allowable, some jurisdictions have a clause that only requires repairs after a failed test and not retesting, or as we like to refer to it as an oopsie clause. However, more stringent code versions require retesting after repairs to prove the repairs work and allowable air leakage rate is achieved. Overall, the trend is for more jurisdictions to require testing, and also more stringent testing requirements, such as no more oopsie clauses. These are the major requirements as of last year. Note that this list is not exhaustive, but it's just to give an idea of where the industry is trending towards. More required testing and lower required targets. Note that some project sites may have more stringent local city amendments as well and government codes that may apply. This is a flow chart showing the different whole building air leakage testing compliance paths in the newest 2024 International Energy Code. Note that adoptions by more states are anticipated to be coming for this as they go through their upcoming code adoption cycles. There's a lot here, but the required path with a code is also project specific, depending on the building's occupancy type, climate, and size. And almost all paths lead to testing in the 2024 International Energy Code. Targets are also changing and becoming more stringent. For example, in 2018, the allowable air leakage rate was 0.4 CFM per square foot. In 2024, that's now updated and lowered to 0.35. Therefore, even with specific codes, number of different paths, the applicable path needs to be determined so that everyone on the project team is on the same page. This graph shows a study by BC Housing and compares three things: air leakage rates of construction with no code requirement, air leakage rate of construction of U.S. Army Corps of Engineering with a 0.25 air leakage rate requirement in the middle, and Washington, D.C. with a 0.4 air leakage rate requirement. Studies have found that by requiring air barrier continuity be verified with on-site testing, the overall air tightness of the enclosure increases, regardless of the required performance metrics from the code. Buildings with no code requirements for air tightness testing did not perform as well, compared to buildings where design and construction team knew that whole building air leakage testing was going to be performed. Overall, what this shows is that when there's a code requirement, it results in tighter, better building, air barrier performance, and that's what everyone likes and wants. This slide shows the industry standards that apply to the whole building air leakage testing. The three most common ones in the US are the ASTM standards at the bottom of this list here, with the most common being the ASTM E 3158. 3158 is the most common, and for larger multi-zone buildings, it's more modern, and it's what's considered the gold standard now. The ASTM 1827 and 779 are historically for multifamily residential, and doesn't handle large commercial or windy days or stack effect conditions as well. The Air Barrier Association of America, or ABA, has made these summary tables. They're hard to read here, but we've put in some images that are good to reference. They summarize the testing requirements in these standards. This is for 3158. And what the test standards allow for overall is repeatability, accuracy, and robustness of test results. Whole building air leakage testing is a high stakes test, and we want to make sure that we're getting it right. These tests allow that if someone tests and then somebody else comes in and tests, the goal is to want a small margin of error, and that's what these testing requirements are for. Keep in mind, the testing standards pass and fail criteria are based off the jurisdiction, and the testing standards themselves, while similar to each other, have slight differences when it comes to building prep, testing limitations, and reporting. And now Justin will talk more about the testing itself.
Thanks, Bill. Yeah, so I'll jump in and talk a bit about how the testing is performed. We won't get too much into the weeds of how to perform the testing, but I do want people to understand what's involved and how to plan for successful testing on a project. So the first slide here is just some definitions for those of you that don't deal with air leakage measurement on a regular basis. In the US, we typically measure air leakage in cubic feet per minute per square foot at a constant pressure. That pressure is typically measured in pascals, so we do mix standard international units and the units that we're most familiar with here, but that's just the way it's done for commercial projects. If you're used to air leakage testing for single and multifamily residential, you may be more used to seeing air changes per hour. And those are just different ways of expressing air leakage rates, whether it's a volumetric rate relative to the volume of the space. For commercial air barriers, the standard is settled on the cubic feet per minute per square foot of building enclosure area. And it's also very important to note that this is, if you think of a cube, it's all 6 sides. So you do include the slab on grade or whatever is, your walls and floor below grade. It's not the floor square footage of the building. So that can be a little confusing if you're not used to looking at some of this information. So Bill talked a little bit about what it is, but in terms of what it is from a operational standpoint, first of all, it's the best method we have of determining a quantitative air leakage number that's repeatable and comparable to other buildings to know how the air barrier is actually performing. It involves the creation of, we're going to create a constant known pressure differential across the enclosure. With commercial testing, we're going to do this at multiple pressures in order to gain greater accuracy and tune out some of the noise from wind and stack effect and other things that can have an effect on the measurements. And we're using some sophisticated fans. A lot of people think, they just look like fancy box fans. They're all computer controlled, highly calibrated, and they're all interconnected. So you're building a computer network on site, and they all go back to a single location, usually called a command center, but it's usually a table with a laptop and a router that's controlling all of these. So that they can be throttled together, because we're usually talking about multiple fans, sometimes many fans, depending on the size of the building. And they have to be able to be controlled from one location and moved in power together in order to efficiently test the building. And then, of course, we're using micromanometers to measure the pressure differences, typically between the interior and exterior of the building. Sometimes if you have, a lab enclosure or, an auditorium separation or something within the building, that might be between two spaces. But usually when we're talking about this, we're talking about the inside to outside delta P, or the difference in pressure. And theoretically, it's pretty straightforward. So what you're doing is, if you imagine a simple section of a building like this, you've got a little bit more complicated than a 6-sided box. But if you assume this box has a bunch of small holes in it, what we're doing is we're pumping in a known amount of air at one location, so that the fans are able to very accurately determine how many CFM of air, the volume of air that they're delivering. And if you're delivering air to an enclosed volume and you're maintaining a constant pressure, as in the pressure isn't continuing to change, then quite simply the air in has to equal the air out in this diagram if you're pressurizing the space. So once we get this to whatever our current test pressure is, and as I mentioned before, we'll be testing at several different pressures during the process, but the reporting pressure, the one that you'll see on the reports, is 75 pascals. That's the upper end of the range that we go to on commercial buildings typically. And so if you're maintaining that building at 75 pascals, either positive or negative, in this diagram it's positive because we're pushing air in, whatever is going through, the total amount of air that's being pushed in by the fans has to be equal to the air that's leaking through all of the holes in the air barrier. And that's how we determine what that leakage rate is. We know that volume, and then we just divide it by the square footage of the enclosure, and that's what gives you the metric. That's kind of the bottom line of this testing. Testing process has a few basic steps to it. Running the test itself when the fans are actually on is actually a very small part of what it takes to do this testing. That's the fun part, and that's when we find out what it is that we set out to know. But there are a lot of logistics and planning that go into this testing. So the first step is just collecting the necessary information. What, as Bill pointed out, what requirement are we under? Are we satisfying a code? Is this purely for diagnostic purposes? Is this something that the architect put in the spec and it's not necessarily based on a code requirement? Does an institutional owner have their own requirements? We need to know what those are. So we need to know, the test standard that we're testing to, because they all have different requirements. And we need to know what the maximum allowable air leakage is, because that will determine that, and the square footage of the enclosure will determine how much equipment it's going to take in order to pressurize and depressurize this building to 75 pascals. And of course, the amount of equipment determines shipping costs, labor to set up and operate it. That's really going to drive the cost of the testing. So we want to know that ahead of time. And also, there's a lot of other logistics related to power and where these things are going to go in the doors. And we'll talk a little bit more about that in a minute. The second phase is whoever's going to be doing the testing, whether it's a building enclosure consultant that's also doing the testing, or if you have a separate test agency, they're going to create the test plan. So they're going to lay out what all the roles and responsibilities are for the people participating in the test. And it's not just the testing agency. It's going to be the construction team, the general contractor. It's going to be probably the mechanical engineer. You're probably going to have somebody on site that knows how to set the mechanical equipment up and knows how to, reset trip breakers, because that can happen. The fans can pull a lot of current. And if you accidentally plug two of them into 120 amp circuit, you may trip some breakers. It won't do any significant. It won't do any damage. You just need to have somebody that knows how to turn things back on. You're going to have to be able to control access to the building. So there's just going to be a number of people interested parties, but also that are necessary to pull off this testing. After the building's set up and you've got all the equipment in place and your data network connecting all the fans back to your central computer, you're going to pressurize or depressurize the building to a number of different constant target pressures and measure the airflow needed to maintain those pressures. And so depending on what standard you're under, usually we test in both directions because you're actually going to get different values. When you pressurize a building, things like gravity dampers, doors push away from their seals. Usually the building gets leakier when you're inflating it, if you want to think about it like that. And when you depressurize, you're doing the opposite thing. You're pulling air out of the building, so you're kind of sucking on the building, and that's going to pull things like gravity dampers and things that press against gaskets and seals to actually get tighter. So typically you're going to have a larger number at pressurization than you are at depressurization. Of course, buildings experience both of those often at the same time on different sides of the building under normal operating conditions. And so the testing standard, all of these standards, if they test in both directions, will average those two values. And the test standards that don't test in both directions typically test only under pressurization. So that's like a worst case scenario. So by averaging them, you actually get usually a little bit of forgiveness down from what a pure pressurization number would be. And then based on that, you're going to calculate the leakage rate. The computer software that runs, that helps you run all of these fans will do all of there's actually some pretty sophisticated math going on in the background in terms of normalizing the data, and it's figuring out the air leakage curve. We won't get into all of that in this presentation, but the software typically does that for you. And so you need to understand what it's doing, but you don't have to do that all by hand, or the testing agency doesn't have to do all of that by hand. And then you get the number that everybody is looking for, and that's that bottom line. What was the leakage rate at 75 pascals? And is it below the maximum allowable? And that's, of course, if you're doing quantitative testing for code compliance or meeting the spec requirement. Otherwise, maybe that's just a number that you record and you're going to compare it after you make repairs to the building, or if you're doing diagnostic testing, you may not really care about the specifics of that number at all. You're just trying to pressurize or depressurize. All right. Simple question that needs to be asked throughout the design process, and certainly before the testing is done, is what are we trying to measure in terms of, what is the envelope or the enclosure that we're measuring? What is the extent of the air barrier? And, if you're thinking about a simple case and you've got a rectangular prism for a building, it's probably just, all 6 sides. But you've got things like stairwells that open to the exterior, you've got mechanical rooms, you've got loading docks, you've got, sometimes equipment rooms and other things that also open to the exterior that often aren't fully conditioned. So what's included there? Where is your air barrier? Is it at the loading dock door, or is it actually at the back wall of the loading dock, because those doors can be open all of the time? So determining that is an important first step, because when you're determining the leakage rate, that's your denominator, right? That's your total square footage that you're dividing by. So that's important to know. And also for diagnostic purposes, what are you really trying to test? The easiest type of building to test would be something that looks like this diagram, right? It's rectangular solid, it's all open. This would be the only buildings that are really like this, or warehouses, maybe some garages or other facilities like that, where everything's wide open. You can put the air wherever you want. You're going to pressurize the whole thing, and it's going to measure the leakage through all 6 sides. That's really what we want to do, and we want to try and make buildings into a single zone if we can, because it simplifies the testing greatly. And by single zone, what I mean is that you're putting the air in at one location, everything is being pressurized at the same time to one constant pressure. In reality, most buildings that get tested look a little bit more like this, whether they're multifamily, residential or commercial office buildings, usually you're going to deliver the air at the bottom, as long as there's not too much stack effect that you're fighting. And the air is going to go to the different floors, usually via stairwells in their doors. But in some buildings, you can only move a certain amount of air through an opening of a certain size before you get a choke point, and you get a pressure drop that's significant enough that the accuracy of your test is no longer comparable to a single zone test. Those buildings can be tested. They're just tested in a little bit different way. You can still treat them as a single zone, sometimes by delivering air at different levels of the buildings via balconies and balcony doors. Usually have on commercial buildings, a rooftop door, maybe coming out of a mechanical room, to try and balance out some of those pressures so you can deliver air to both sides of wherever your choke points are. But we won't get too much into that today. And then sometimes buildings are just too chopped up or large to test that way. A good example would be a high-rise building. It just wouldn't be practical to deliver enough air distributed along the height to test a building like that. Because typically high rises are office type buildings. They don't have that many balconies. There are exceptions, of course. So you can only put in air at the bottom, maybe at the top. But you're going to have a lot of choke points down the building, and just the volume of the building would require an enormous amount of equipment. So there are other ways to do that. And whenever you've got something like that, you can test floor by floor. The standards do allow for this. And you usually have to test a certain percentage of the floors, but you definitely have to test the first floor and the top floor and the ground floor, because that's where the bottom piece of your air barrier is, and the lid of your air barrier is at the top. But you do that with a series of tests. We call this guarded multi-zone testing, where essentially, if you were going to start at the top of the building, if you pressurize that top floor, you're going to be measuring the leakage out of all 6 sides. And we don't want to measure the leak. We just want to know the enclosure leakage. And so we want to essentially zero out the leakage across the floor. And so the way you do that, air leakage, you have to have 3 things. You have to have air, you have to have an opening, and you have to have a pressure differential across the opening. If you get rid of any one of those 3 things, you don't have air leakage. So we can't really get rid of the air. We can't get rid of the opening. That's what we're trying to measure. So what we can do is balance the pressure across that opening. So what you do is with another fan that's run independently, or series of fans, depending on the size of the space, you're going to balance that pressure. And so in this diagram, it's showing 50 pascals on both sides. What that's going to do is going to zero out the leakage across there, and whatever that top fan, the delivered air volume drops by, you can essentially subtract that out as the floor leakage, and you now have just the exterior boundaries that you're trying to measure. And of course, you can do this in 3 dimensions. Sometimes it can get quite complicated. And again, don't want to bog down with those type of details right now, but it can be done. It is more complicated and requires more planning. But it is an option for buildings that can't really be tested as a single zone. This is an example of a sheet from a test plan. Typically, at least the way we like to do ours, and I think a lot of testing agencies do this way, we want to lay out exactly where the equipment is going to go ahead of time, and make everybody that's part of the testing be aware of that. So we want to know, first of all, where are we going to put the fans? We've already calculated how many fans we need. But how are those fans going to be set up? How are pressure measurements going to be taken? Where are we going to run tubes? How are we going to run the data cables? And how many hundreds of feet of Cat6 cable are we going to need? But maybe the most important thing to determine ahead of time is where we're going to plug the fans in, because each one of these fans typically needs its own 20 amp circuit. That can be a challenge. And so it can more often than not be accommodated by the building with careful planning. Sometimes you have to do things like bring in generators, but we want to have that worked out ahead of time. The building has to be prepped. So typically we're doing what's called an enclosure test and not an operational test. So there are certain openings in a building, primarily air intakes and exhausts. They're intentional openings in the air barrier, and we don't want to count flow through those during the test. So dampers do get closed, but dampers, there's no damper that's completely airtight. And some of these openings, don't have dampers on them. So those will get sealed, usually with plastic and tape. And sometimes for bigger openings, you have to, go to plywood or foam panels or something like that. But that all needs to be planned ahead of time, and who's going to do it and who's responsible for that. Once the building's set up, you've got all your equipment set up, and if you look over the shoulder of the person that's running the test, this is probably what you'll see, or another version. There's two main manufacturers, and they both have their own software, but they both basically do the same job. But you're going to see a live feed of all of the pressure measurements and flow measurements from the fans. And these vertical rectangles are going to be the data points that are being taken. And you don't really have to know what any of that means, but at the end of the test, this is the output, typically directly from the software, and it's figuring out the flow curve, but it does graph it as a straight line. The reason it does that, it's a logarithmic graph, so it takes a curve, and the resulting graph is a straight line. The red dots are going to be the data points that were taken at the different pressures. And what you really want to see is those red dots all strung along that line, like beads or pearls, because that means that they're all in very good statistical agreement with one another, and the data is very clean. You will see them bounce around a little bit. This data is exceptionally clean. It doesn't always look like that. There are some numbers on the kind of middle right. You'll see correlation coefficients R and R squared. Those have to be above a certain threshold, depending on the test standard, that basically determining that the data that you have is good enough and meets the accuracy requirements that have been determined through research. And ultimately what we're looking at is that blue number. The bottom line number is that blue number. You'll see test one pressurization. It says 0.143 CFM at 75 pascals per square foot. That's a huge number. Most of our code requirements today are 0.04. This was of an existing building, so didn't have to worry about meeting a code requirement. But that's the number that we're looking for. Real quickly, we'll move on to diagnostic testing. So diagnostic testing is when you're doing quantitative testing, you're determining an overall average air leakage rate through the entire building air barrier enclosure. Diagnostic testing helps you find where the actual leaks are located so that you can do something about them. This can be done on existing buildings. It can be done on new buildings, especially if you're not meeting requirements. And as long as you can produce differential pressure with a differential temperature, you can get results through a number of different methods. And those methods are outlined in ASTM E1186 for air slide leakage detection. I'm here with a temperature differential. This was a cold weather evening. So you've got cold air outside. You need at least a 10-degree Fahrenheit difference between the interior and the exterior typically. And then we'd like to do this with about a 25 Pascal difference. Different people have preferences for different pressures and what they're used to and seeing. And you're looking for the effect that air leaking, in this case, we're pressurizing the building. Warm air leaking out is going to change the surface temperatures adjacent to where the air is leaking out. On the left, this is actually where we were depressurizing. So this would be pulling in cold air through any openings. You see that at this unsealed vent penetration. On the right, you'll see, this is a telltale pattern around a roll-down door, which are notorious leakers, and you can see where the warm air is leaking out because this is under pressurization. And then the reason that we run it in both directions for this IR imaging is because you're going to get differences in surface temperature, not only from air leakage, but you're going to get them just from the difference in the resistance values of the assembly. So you don't always know, like on this left-hand side, you've got this metal panel enclosure with these seams that are clearly warmer, same building, cold day, we're pressurizing the building. So we're looking for warmer spots. Seams and panels would be a likely location for air leakage. But how can we be sure that that's not, some kind of, there's no insulation, where the seams butt up against one another. There could be a number of other reasons for that. So what you do is you test in one direction, take your images, then you turn off the air pressure, let it sit for 15, 20 minutes. That's usually enough. It depends on whether or not you've got a thermally massive enclosure or not. Metal panels change temperature back to ambient conditions pretty quickly. Then you run it in the other direction. And what that does is, if it was air leakage, that those warm spots are going to go away. And if it was just due to a resistivity difference in different parts of that image, then that image will stay the same. And so that can help you narrow down whether or not it's an air leak or it's something else that's going on. Another very straightforward way is to use theatrical fog. Some people, we call them smoke pencils, other things. It's really theatrical fog. They don't let us burn things anymore like they used to do in the old days, which is good. And this is great, especially for show and tell, or if you've got a suspect area, especially if something shows up in the IR, you can go back with the theatrical fog. Typically pressurize the space and apply the fog at the interior side of an area that you're interested in and see if it comes out the other side. Pretty straightforward, but a very good method, and very good to demonstrate where the air is coming out for those that have to repair it. Now, just a couple of quick testing examples from the field, just to show some different types of tests. This was a historic library in Massachusetts. They were going to be doing renovations. They knew that it was air leaky. They wanted to improve that as part of the repairs. They wanted to be able to benchmark the existing performance in a number of different ways and compare it before and after. So just to give you an idea, this is the equipment that we shipped up just for that test. This was an 10-fan test, so relatively large, but you can see just the amount of equipment that has to be shipped in terms of logistics. In the case of this building, it tested out to 0.745 CFM at 75 pascals. That's not really that unusual or terrible for a historic mass masonry building with old wood sash windows that was never designed to really have an air barrier with air tightness in mind. Today's modern code standards are usually 0.4 or tighter. So, it's roughly twice as leaky as that, but it just means that they had a good amount of room to move with their repairs. But of course, we did a lot of diagnostics on it, because that's what the design team really wanted to know is, how do we address this? How do we develop a repair plan? So here are some IR images, one on the left with infiltration, again, this cold weather during the wintertime, and the one on the right was with pressurization. And you can see the warmer spots, particularly up towards the top of the building. And then, of course, while we're doing this, we're notating where these are, and then going back and identifying with fog, or some of these areas you can just go up and put your hands in, but we're notating all of that so that we know which details need to be addressed in the next phases of work. In terms of guarded testing, in multifamily, this is done a lot. This is actually a resort in the South Florida area. They were having humidity control problems. They wanted to know, is it the enclosure or is it leakage between units? So in order to do that, we had to do guarded testing. so that we could get all of those differing values. In this case, you can see, if this was a 4-story building, if you're interested in a room on the 2nd floor and you wanted just the enclosure values, you actually had to put fans in that room plus the 2 on either side and the 1 on top and bottom. And then all of those get controlled independently. And it can be quite complex, even though you may only have 1 fan in each room. It's very interesting testing. You can get a lot of different information about the relative leakage between adjacent spaces. So that was a good test. And of course, during that testing, we're also doing diagnostics with a smaller fog generator, in this case, around the base of a sliding glass door, which are notorious for not sealing properly once they're in operation, and then also taking some differential measurements across some fur downs and other things that you can do as diagnostics in conjunction with your whole building testing or your compartmentalization testing, as this would be. The last one, really big building. We think this is the biggest building that has been tested in North America. We're not entirely sure because there's no real place that reports that. So I'd love to hear if there is another one, but this was 4 million square feet, a distribution warehouse in the Northwest, very large. You can see the volume on the inside. The building just kept going. It's 4 stories, but the great thing is it was an easy single zone because everything was very open between floors and across floors, just a lot of distance. We had thousands of feet of cable. There weren't enough outlets and power sources, so we did have to bring in generators and power points in order to test it. When you do the calculations on this for a standard blower door fan, it came out to requiring about 80 fans. I'm not aware of any test agency in the world that has 80 fans themselves. So we had 4 different partner companies on this test. Which was great because it's a small world and we all love working together. But still, 80 fans would have been a push. So what we ended up having was somewhere in the neighborhood. I think we brought 30 fans to the site, but we engaged a partner out of Minneapolis that has, I think they're the only ones that have these fans. They're these very large industrial fans. They're the equivalent of about 25 standard blower doors a piece. So these 2 together accounted for the airflow of 50 fans, and they're pretty interesting because they actually run off of a modified V6 car engine. So that's always pretty cool. But of course, a lot of logistics and costs. These had to be driven from Minneapolis up to the Northwest for this test. But really interesting test. Tips for successful testing, just to sum up here. During the design phase, you wanted to determine your testing requirements and specifications early and include all of those details in your document so that everybody knows what to plan for, that the general contractor knows what they're bidding and what they have to accommodate in their schedule. You should, if possible, graphically identify the 3-dimensional extents and square footage of the air barrier. Remember all 6 sides. It's one of the common mistakes we sometimes see is not including that. Usually the bottom is what people will leave out of those calculations. This helps you identify potentially problematic transitions that need to be further detailed within the drawings to help ensure continuity. And ensuring continuity is the name of the game in air barriers. So anything we can do to address it, it's usually those transitions between systems that tend to be the most vulnerable to air and water leakage. It's a good idea on especially large commercial work to engage an experienced building enclosure consultant that may or may not also do the testing. It's good to bring on whoever's going to do the testing early, even if it's just to do the planning and there's going to be a long time before it's executed, because you really do have to, you need that testing plan so everybody knows what they're going to have to do. You can line up schedules. You can build it into the schedule for the building because you're going to have to essentially shut the site down, whether it's a an operating existing building or the building under construction, you have to be able to control access and not have people opening and closing doors, and you're going to be blocking some of the access with fans. And so that all needs to be planned for. A lot of this testing gets done at night. You'll notice in some of the photographs that it was nighttime, especially in existing buildings. They like to not have to shut down during the day. So we do a lot of testing at night. During construction, you utilize a robust QA/QC program for the air barrier systems. That can be included as part of the building enclosure consulting. ABA also has, the Air Barrier Association of America also has a great quality assurance plan that can help with that. And then have a contingency plan for testing. What do we do if it fails? What do we do, if there are thunderstorms? That sometimes things don't always work out exactly right. So you've got to accommodate that in your scheduling and your planning as well. And it's a team effort. And so this is the team from that large warehouse test. And yeah, it's always fun working with a lot of great professionals. And so with that, we'll wrap up and I'll hand it back to Liz. Thank you.
All right. Thanks, Justin, and thanks, Bill. That was a great presentation, lots of information. We are running a couple minutes behind today, so we will extend a few minutes past the end of the hour to answer your questions. If you're not able to stay with us until the end, please note that you'll receive an email this afternoon from us with a link to re-access the webinar console, where you can watch an on-demand version of today's webinar, download a PDF copy of the slides, and your certificate of completion. Okay, let's take our first question. How would a test plan be created for a multi-unit space building, such as a condominium? Would every individual unit have to be tested?
No, not typically. It depends on what standard you're under. They have different requirements that are outlined. Usually you would have to do, it depends on how big it is. I mean, if you're talking about like a 4-unit, small like townhouse complex or something, you would probably test all of the units. Bigger ones, it just depends on the layout, but the answer is, unfortunately, it depends. There are different ways to lay out those buildings, and you can do it through guarded testing, but usually the larger buildings that you can't treat as a single zone, you would test almost like you would a high-rise, where you've got to test a certain number of representative units, and you have to catch the end units and the ones on top. Again, it depends on the standard and what it requires.
Okay. Our next question, can testing be performed while the building is occupied and in use?
Only if you can keep people from going in and out and you have enough surplus exits to meet fire code requirements. And that is usually not the case. And so my general answer would be no. It's not going to affect the test itself. If you're inside the building during the testing, like, you don't feel the pressure difference. So it has nothing to do with that. It just has to do with people coming in and out and just basically fire evacuation safety.
Okay. At what stage in the construction process do you recommend testing, before or after the exterior cladding is installed?
Sure. So in a perfect world, you would do it before the exterior cladding was installed. Once the air barrier is complete and you've got all your door seals and all your windows in. Unfortunately, the way that sequencing for most commercial construction, or most construction in general, works is it doesn't quite go in that order of operations. So usually the cladding is up and the building is nearing completion to have all of the necessary air barrier components in place. But in a perfect world, you would do it before the cladding went up. That way, when you do your diagnostics, it's a little bit easier to see directly the holes that are causing the leaks, and it's much easier to repair. One of the reasons you want to make sure that you have a good design and QA/QC during construction program on the air barrier is this is a high stakes test. If you fail it, and there's no, I think Bill called it an oopsie clause, where they kind of let you do some diagnostics and then just record the number and go on. Most of them aren't allowing that in the more modern requirements. Yeah, I mean, you're talking about potentially tearing cladding off to get to some of this stuff, or taking down soffits to look for beam penetrations, and all kinds of things. And so if you can have everything exposed, it's a better situation. But unfortunately, the sequencing and scheduling doesn't usually allow for that.
Okay. What does an air barrier shop drawing look like?
So that's a very good question, because the air barrier is made of components that are usually done by different subcontractors. So you usually think about shop drawing submittals. You've got your curtain wall shop drawings, you've got, your waterproofing shop drawings. And so usually what ends up happening is you either have to, the GC either has to do coordination drawings, or you have to have, it's very tricky, and rarely do we ever see kind of a complete set of air barrier drawings. They usually come from whoever's going to be doing, actually applying the air barrier, but they have to coordinate with roofing and the other trades. And so you have to make sure in the specifications you're very clear that they have to coordinate those details with the other trades. So that's usually what it looks like, is whoever is doing that air barrier material is going to be responsible for that. But it requires additional coordination and the participation of subs with other pieces and components that comprise the air barrier.
And one of the other things I've seen with that is that the air barrier shop drawings, it'll call out specific materials and the different accessories with an air barrier system, let's say at an opaque wall. And then where it transitions, let's say with base of wall at the waterproofing, it'll show different layering with the different waterproofing materials. And then, things will be asked of, adhesion and compatibility between which materials are going on top of other materials and sealants. So that's something else that we've seen.
Okay. For diagnostic testing, do you pressure the building and put the IR camera in the interior, and then do the opposite for the exterior?
So if you're pressurizing the building, the IR camera is going to be on the exterior, typically. And then if you're depressurizing, you're looking on the interior, because that's the direction that the air is flowing through, and that's where you're going to get your best images.
Okay. Can you pressurize a building utilizing its own HVAC system?
So yes, and for diagnostic testing, we actually, especially for larger buildings, if we can get the mechanical engineer and/or the building staff that know how to operate those systems to create, if they can get about we like at least a 15 Pascal difference. I'd rather see it 20, 25, or even higher. In at least one direction, then you can use that for your diagnostics. We'd like them to be able to do it in two directions. It's not always possible. However, for quantitative testing, you really can't do that. There are some standards. I don't remember if 1827 still has that option in there. But the problem is there are a lot of great people that develop these testing protocols through a lot of research and a lot of experience over about the last 50 years. And what they've determined is that the accuracy of the flow measurement through the mechanical system, even if you do things like pitot tube traverses, and for those of you that are familiar with airflow measurements and mechanical systems, or using the built-in monitoring that some of these systems have, that they're like plus or minus 20% in terms of their accuracy, or numbers that I've heard tossed around. But they're huge deltas in the accuracy of those types of measurements, and it's been determined that that's just not good enough for something that's high stakes, and it needs to be more accurate than that when you're actually talking about how much air is leaking through a building enclosure. So yes, for diagnostics, if you can find somebody that knows how to essentially get the mechanical system to operate in a way it really wasn't intended to safely, but not for quantitative testing.
Okay, this person said, I've heard of a new technology which identifies air leak locations in a facade using sound, i.e. speakers and microphones, with the idea that sound leaks equal air leaks. Have you ever used or heard of this?
So yes, definitely heard of it. I've seen it demonstrated, and I believe we actually have one that we've used for our own internal testing. I haven't played with that myself. That technology's been around for a while. It's actually mentioned in ASTM E1186. I think it's still in there. I guess I don't have much of an opinion on it other than I'm sure it has its place. It can't be you can't, from what I know, you can't like broadcast a sound through a whole building and then walk around with, some kind of, they have these sound cameras now and other things that I don't have a full understanding of the technology, but I'm not aware of anybody that does this type of diagnostic testing regularly on large commercial buildings that I see them bring those out. I think if you've got a localized area where you've got a pretty good idea of where the leakage is, that and some other technologies that have come to the market in recent years or are under development in some of the research labs can be helpful. But yeah, that's kind of the limits of my understanding of using an acoustic method like that.
Okay, we'll take one more question. When not required by code, are you seeing the requirement for whole building air testing written within project specs become more common?
Yes. I think as more designers and owners become aware of the testing and with, this evolving shift that's been happening for years and years and years, of increasing scrutiny on energy usage. And as we tighten up buildings for energy usage, that also creates more moisture problems. The two can often go hand in hand. There's a recognition that the air barrier is incredibly important to the performance of the building. And this is the only good way to test that performance and hold a design and construction team to a specific performance standard. It can, and that also helps them, right size the mechanical systems during design and other things. So we are seeing some of your more, I hate to use the word sophisticated experience, like your institutional owners you see it a lot more in their specs. The Army Corps has been doing it forever. That's why they've got their own standard. They kind of had the first big building standard that's been around for a very long time. So yes, we are seeing it more and more. The bulk of what I'll call compliance testing, though, is being driven by code requirements, but we do see it independently in the specs. We're also seeing a trend where owners are starting to require actually more stringent test targets for certain projects than what's strictly required by code. So that is happening as well.
Okay. All right. Thank you, Justin. And thank you, Bill. It was a great presentation. We got lots of good questions, far more than we could answer during the allotted time today. So if we didn't get to your question, please be on the lookout for an email from Justin or Bill in the next week or so. They will follow up and try to answer your questions directly. Thank you all for joining us today, and thank you for hanging around a little bit longer. We hope it's been educational. So again, thank you so much for your time, and we hope you have a great rest of the day.